This video is about what happens when you take multiple discounts on an item, or sometimes if there's a percent increase followed by a decrease or the other way around. And so cumulative discounts. Your friend arrives at your house in a foul mood. Today's newspaper contained a 20% off coupon from Old Navy. The $100 jacket she had been eyeing all season was already reduced 40%. She clipped the coupon, drove to the store, selected her jacket, and walked up to the register. The cashier brought up a price of $48. Your friend insisted that the price should have only been $40. The store manager arrived and re-entered the transaction, and again the register displayed $40. Your friend left the store without purchasing the jacket and drove to your house. How do you think your friend calculated a price of $40? So $40 meant that the amount that she discounted was $60 and that she was only paying $40. And so she calculated a 60% discount, and the way that she calculated that 60% discount was the 20% off coupon plus the 40% off sale would give her a 60% off. So this is not how this happens when you go buy something. There's a 40% off sale, and then they take any coupons off of that 40% sale. They don't add the percents together. And so in this problem, after your friend calms down, you grab a pencil and paper to start your own calculations. First, you determine the ticketed price that reflects 40% reduction, at what price Old Navy is selling the jacket, and then explain how you calculate this price. So you have a $100 jacket. It's being reduced by 40%, which means you're paying 60% of that, and so your decay factor is 0.6, so you multiply that by 0.6, and that is 60. So they're selling it for $60. To what price does the 20% off apply? Well, this applies to the $60 from number 2. Apply the 20% discount to determine the final price of the jacket. So we're going to take that from the $60, and if you have a 20% off or 20% discount, that means you're paying 80% of that, and so we're going to multiply by the decay factor of 0.8. And when I take 60 times 0.8, what we get is the $48 that the cashier had calculated originally. Now you're curious, could you justify a better price by applying the discounts in the reverse order? That is, this should be the word that. That is, applying 20% off followed by 40% off. And so let's start our calculations over again. So if we applied the 20% reduction first, so that would be the decay factor 0.8. That would bring me down to $80. And then in problem 6, you want to apply the 40% off, so that would be the decay factor of 0.6. So multiply 0.6 to the 80, and that gives us $48, just like before. So it doesn't even matter what order you apply the discounts in, you still are going to end up with the same amount. And so this one is to write a sequence that gives us the sale price, or which sequence gives us the, I'm trying to rush. In number 7, which sequence of discounts gives a better price, and they are the same. So mathematically, the reason that they're the same is if you take 100 times 0.8 times 0.6, it doesn't matter what order you do this multiplication in, you'll still end up getting the same result. So you can form a single decay factor that represents the cumulative effect of applying the 3 consecutive percent decreases. This should be 2. is a single decay factor, and that's the product of the given decay factors. So just like I was talking about right here. So you can multiply these two together to give you a single decay factor, and however many discounts or increases there are. Determine a single decay factor that represents the cumulative effect of consecutively applying Old Navy's 40% and 20% discounts. So that would be 0.6 times 0.8. And when we multiply 0.6 times 0.8 on our calculator, we get 0.48. Use this decay factor to determine the effective discount on your friend's jacket. Well, so this would mean that we were taking off a discount of $52 would be the total effect. And so we would be taking 52% off. Now we're going to determine a single decay factor that represents the cumulative effect on consecutively applying Old Navy's 40% and 20% discounts. So the 40% was 0.6 for a decay factor, and the 20% reflects a decay factor of 0.8. So when we multiply these together, 0.6 times 0.8, we end up getting 0.48. So this is the decay factor, and so that's the part that's remaining. The discounted price is going to be 0.52, and so use the decay factor to determine the effective discount on your friend's jacket, and so that would be 52%, not the 60% that she had originally thought. Right, so this is the amount that it's decaying by, and this is the amount that is remaining. Sorry, I had that backwards. This is the amount that's remaining, and this is the amount that it's decaying by. Determine a single decay factor that represents the cumulative effect of consecutively applying a 40% discount and a 50% discount. So the part that's going to remain from the 40% is 60%, so that's 0.6. And the part that would be remaining from a 50% discount would be 50%, so that's 0.5. And when we multiply 0.6 times 0.5 on our calculator, we get, whoops, that wasn't right, I don't think. 0.5 times 0.6, and we get 0.3. Use the decay factor to determine the effective discount. 0.3 would reflect a 70% discount. So that would be 30% that was remaining, and the discount would be 70%. Your fast food franchise is growing faster than you'd ever imagine. Last year you had 100 employees statewide. This year you opened several additional locations and increased the number of workers by 30%. With demand so high, next year you will open new stores nationwide and plan to increase your employee roll by an additional 50%. To determine the projected number of employees next year, you can use growth factors to simplify your calculations. Determine the growth factor corresponding to 30% increase. Well, that would be 1.3. Apply the growth factor to calculate your current workforce. 100 times 1.3 would be 130. Determine the growth factor corresponding to a 50% increase. That would be 1.5. Apply that growth factor to your current workforce to determine the projected number of employees. So we have 130 employees currently, and we multiply that by the 1.5 growth factor. And it gives us 195 employees. Starting from last year's workforce of 100, write a single chain of multiplication to calculate the projected number of employees. So that would be 100 times our first growth factor of 1.3 times the second growth factor of 1.5. And so if you calculate that out, you will get 195, just like we got doing it in 2 steps. So again, you can, this box is just saying that you can do a single growth factor by multiplying these two things out. And so if we do that, take 1.3 times 1.5, we get a growth factor of 1.95. So that would be an increase of 95%. What goes up often comes down. You purchased $1,000 of a recommended stock last year and watched gleefully as it rose quickly by 30%. Unfortunately, the economy turned downward and your stock recently fell 30% from last year's high. Have you made or lost money on your investment? The answer might surprise you. Find out by solving the following sequence of problems. First, to determine the growth factor corresponding to a 30% increase. That would be 1.3. Determine the decay factor corresponding to a 30% decrease. Decay factor there would be 0.7. And we can form a single factor that represents a cumulative effect by applying the consecutive percent increase and decrease. The single factor is the product, again, of the growth, decay, or growth or decay factors. Does 0.91 represent a growth or a decay factor? And it's decay. And how do I know that? Because it's less than 1. What is the current value on your stock? So we had $1,000 was how much our stock was worth, and then it grew by 30%, so that's an increase of 30%, or a growth factor of 1.3, and then it decayed by 30%, so we'd multiply that by 0.7. So in our calculators, we take 1,000 times 1.3 and then times the 0.7, and we end up with 910. So the current value is $910. What is the cumulative effect as a percent change of applying 30% increase followed by a 30% decrease? And so if you just take the 1.3 times the 0.7 and multiply those two together, what do we end up getting? 1.3 times 0.7 gives us 0.91, and so this is a decay factor, and it's decaying by, so you can take 1 minus 0.91, and that would give you, as a decimal, how much it decreased by. So 1 minus 0.91 gives us 0.09, and so this would indicate a 9% decrease. What is the cumulative effect of a 30% decrease had been applied first, followed by a 30% increase? Well, to do that calculation, it would be 1,000, and then decrease would be a decay factor. 30% decrease would be a decay factor of 0.7, and then times if it increases by 30%, that would be a growth factor of 1.3. And again, it doesn't matter what order you do this multiplication in, and so you're still going to get the $991 or $910 that we got before, because it doesn't matter what order you do your multiplication in. Let me fix that. Okay, so that ends the lecture on cumulative growth and decay factors. Let me know if you have any questions. Thanks.